without much ado, I want to now, it's almost 4:10, and I want to introduce the next speaker, Josh Pereyda. And the one thing I can tell you about him is we met at the Rapid 7 party, and he had, hey, are you Ming? I was like, yeah. He's like, dude, you owe me money. I was like, what the heck? And we met, and I can tell you right now that but based on talking to him, we are very lucky to have him because I can just sense the energy in him. I know I can sense the energy in him. He's very passionate about what he does. So without much ado, please give a warm welcome to Josh Pereyda. Go get him, Tiger.
Thank you. Thank you, Ming. Thanks for coming, everybody. I know there's a lot of always good stuff happening at DEF CON, so I appreciate your time today. We'll get right into it. So the title of my talk is Network Protocol Fuzzing for Humans. I spent the last year or so at work researching and implementing fuzzers, working with both commercial and open source tools. And I found on the open source side, for the most part, the tools were immature. And I should say network fuzzing tools. There are some good fuzzing tools in other categories. But these tools were immature, and I also found that there was a pretty typical development life cycle for fuzzers. You could call it the fuzzer development life cycle. So step 1 is to build a fuzzer. Step 2 is to talk about your fuzzer at some big conference. And step 3 is to abandon your fuzzer. The end. So that was a pretty successful business model, apparently. So when I would try to use these tools, actually download them and work with them, I found either a lack of documentation and tutorials to get started, and typically a lot of bugs or issues that made it hard to do what I was told would be pretty easy to do. So to talk about fuzzers in general first, the theme of the conference obviously is Rise of the Machines. So here's the scenario. You're organizing a resistance to the robot army, rogue AI, super distributed hive mind enslaving overlord MatrixNet. You organize disparate and coordinated fighters using a high-tech, encrypted, decentralized communication system riding on covert channels. Good job, super programmer. So the night of the attack, the Earth stands in suspense as the fate of the world hangs on a few brave souls and one lone programmer, you. Everything so far has led up to this, the final battle. And the machines send a message with a bad header size, causing a buffer overflow, RCE, and there's a worm and your locations are compromised, you lose. Robots win. And all your fighters are shipped off to hominid reprogramming camps. So what went wrong? Humanity lost. What happened? Well, you forgot to validate the header length in an untrusted network packet. So if you've done network programming, you should know that if you're developing software, anything that comes in off the network is untrusted. You need to treat it as malicious, as potentially malicious. Anything that comes in could come, you don't know where it's coming from. And it's an easy thing to forget about as you're actually writing the software because you don't think about the assumptions you have because they're assumptions, right? What else happened? Well, you should have validated your network packet. Also, you should have fuzzed your application. So network fuzzing is good for catching these sorts of vulnerabilities. They're the sort of, actually the typical way to attack a network application is the sort of thing that fuzzing would catch, depending on how advanced your fuzzing is. So could the fate of humanity really ever hang on my little application? Isn't that kind of unrealistic? Well, no. Millions of systems, including the world's biggest internet empires, such as Facebook, once stood vulnerable to this kind of error. It was known as Heartbleed, and it was around for about 2 years. So there's a very critical vulnerability. It's out there in big applications, very widespread, very popular software, and it was there sitting around for 2 years. And well, why in that case there was a programming error, and why else there was immature fuzzing in that project, and you could say in the open source community in general, there's immature fuzzing. So Fuzzing Refresher, how many of you guys have heard of fuzzing before? Okay, most everybody. How many of you have tried to use a fuzzer or work with fuzzing hands-on? All right, quite a few. Cool. So the core concept is to manipulate system inputs to uncover implementation errors. And you could tack randomness onto that, but it's not always random. So what can be fuzzed? Well, protocols, file parsers, GUIs, libraries, and APIs are all things that can be fuzzed. And the common thread in those is exposure to untrusted input and a relatively complex interface with lots of possibilities, lots of things that can go wrong. So you think about a GUI, you could have 50 buttons on the screen, right? You open up Microsoft Word, there's 50 buttons there. You click on one little button, then there's 20 more buttons. Right? And then you click on another one, there's 10 more buttons. And so there's a very fast combinatorial explosion of possibilities, right? This way and that way, and there's too much to test by brute force. Similarly with protocols, there's a structured input that's expected, but really anything could actually come across the network, right? So you program for that structure, you make a lot of assumptions, and it's easy to make mistakes. So a brief history, it was developed by Barton Miller at University of Wisconsin-Madison as a class project, actually. The first fuzzer fed random input over the command line to Unix tools, and it would crash these Unix tools. Big name tools like Emacs, VI, Make, FTP. I think I've telnet on there twice. Oops. Miller himself was surprised at the number of failures that he found using this method. So I guess he didn't think he would find that much, and he thought, oh, quite a big chunk of these big name tools can actually be hacked. And the key development here is using randomness to violate assumptions. And it's if you stop for a second, it's pretty profound, right? So you've got these early world-renowned, cutting-edge Unix programmers. You could call them the mighty men of old, the men of renown, the superior men of yore, the legends, the predecessors, the forerunners, and the people who used computers before it was cool. Their software, the guys with long hair and strange names, their software can be beaten using completely random input, right? So in a sense, the best of humanity kind of is defeated by random input. So you can see why he was surprised. On the other hand, it makes sense because random input is exactly what those programmers weren't expecting when they designed a tool for human usage. They're expecting human errors, not random errors. So moving on, the next big development was around 2000 at a university in Finland, and there's a master's thesis published in 2001 if you really want to get into this stuff. They found vulnerabilities in 40 out of 49 products, and they moved from the command line to fuzzing on the network. So they're attacking protocols rather than specific tools, which is nifty because once you do that, you can attack multiple products if they use the same protocol. 14 of those products were vulnerable to remote code execution, and they switched from complete randomness to using a structured approach, which people call smart fuzzing or generational fuzzing, or structured. There's not really a good name for it. People do smart fuzzing and dumb fuzzing, and it's not really fair because dumb fuzzing isn't necessarily that dumb, right? So here's a demo or a sample of a packet structure. So that's the IPv4 packet. You see the fields there. So a generational fuzzer will look at these fields one at a time and manipulate each of them. So in IPv4, what's the versions field supposed to be? Anybody? Yeah, 4. So what happens if we change it to 5 or 0? You have the total length on the right-hand side, and then IHL stands for initial header length. And so they're coupled values, right? They should correspond because the total length includes the header length. Stop me if I'm getting this wrong. So if you change one value, then it's out of sync. So if your software reads the initial header length and trusts it, or if it reads the total length and trusts it, you can get weird things happening. Or you can just make the length smaller than it's supposed to be, have a big packet, and that's an obvious possibility of a buffer overflow. So the key thing that this tool does is it knows about the protocol, and it will generate these millions of test cases as is appropriate for the protocol. So a typical test case they'll send the anomalous message, the unit might respond, or maybe not if it's a garbage packet, and then you need some way of monitoring whether the unit you're testing is alive. Right? So one way to do that is with the request and response. So you'd send a valid request after your corrupted request and see if it's still alive. And then if not, it failed. So that's generational fuzzing. Moving on to mutational fuzzing. And mutational, you start with a sample of valid data and you mutate it without actually knowing what the protocol is. So you'd still have this packet, but the fuzzer would not know about the structure. AFL is a popular fuzzer, and it's in this mutational category. It doesn't know what the packet looks like. It just pokes at it and mutates it either randomly or using some kind of heuristic, some kind of way of guessing. The obvious advantage of a mutational fuzzer is it's easier to use, or you don't have to program it for the protocol itself. Right? Downside is it may not be as thorough. And then you can also couple it with code coverage evaluation, so you basically have an evolutionary algorithm, and the selection is your code coverage ability, and then the mutation is obviously mutating what you're testing, so you can get some pretty good results with that. So really quickly, comparison between mutational and generational. The mutational doesn't know the protocol, generational does. Mutational is less work per protocol. Generational is more work, you'll spend more time with it. Mutational doesn't have as many bugs, but it has a better bugs to work ratio. And so if you're doing fuzzing, this is the key thing to keep in mind. If you just want to find the most bugs the fastest, you would use something that's mutational, most likely. If your goal, however, is to find the most bugs absolutely, for example, if you're in the defensive case, right, you don't just want to find a couple bugs and tell your boss, I found a couple bugs. You want to say, hey, I'm pretty sure there's no bugs, or there's a certain class of bugs that we've eliminated using this technique. So because generational is more work per protocol, it tends toward the defensive use case, where you're going to put a lot of work in to secure this particular thing. With offensive, you don't care, you just want to find your bug and get your hack. So they're both valid tools, just different emphases. So recap, fuzzers have random input, they find bugs. Hackers like bugs, so hackers like fuzzers. Businesses want to find bugs, so they like fuzzers too. And so you have commercial tools selling fuzzers to those businesses. And they're all in the generational smart fuzzer use case because they're selling to defensive people. Open source tool is the most popular by far is AFL. You guys heard of AFL? Just a few? Really? Huh? Okay. Well, it's from what I can tell, it's the most popular tool right now in the fuzzing category. American Fuzzy Lap is a bunny. It's very good. It's for mutational. It's used a lot for, from what I can tell online, libraries and APIs, and also for GUIs. And you can use it for other things, but it has that API emphasis from what I've seen. Peach Fuzzer was popular. It was forked to a closed source project by the corporate sponsor, so they put an axe to the open source community. So you can still get the several years old version if you want, but who wants to do that? And no diss to the company, most companies don't release any open source tool, so good for them. Spike was superseded by Soli, which is kind of state of the art in generational network protocol fuzzers, and maybe you know one that's better and you can come tell me afterwards or in the question time. But that was, in all my research, this was the best one I could find. there was a good talk on it. If there's a Black Hat talk, I think, from 2007, that'll tell you all about it. And there's a million other tools that nobody else uses. So the open source generational fuzzers, that defensive use case, so the way I got here was not trying to break things so much as working for a company, right? So they're interested in fuzzing, they're interested in defensive things. So I'm in this defensive use case, and I'm looking at the tools, looking at commercial and open source, and the commercial ones are pretty pricey. So it's like, well, you know, maybe it would be worth the time to make it ourselves. But I found that it was not quite there yet, and I'll get into the details more. But first, the why the immaturity? Well, some tools lend themselves to a proprietary model more than others. Tools that are very valuable to a few people, expensive to develop, and in low demand in the open source community. Well, that's a ripe market for commercial tools. So if you want to sell a tool, you can think about that. Most defensive security tools fall into this realm because your open source project doesn't typically have that emphasis where people are going to pour a lot of time and money into marginal security increases. Other tools could be open source but are plagued by anti-incentives, mostly commercialization. That's Peach, right? Kind of was open source, not anymore. They still sell it. And then there's a business desire to keep your methodology secret. I think Microsoft comes into this category, so they've published a lot on fuzzing. They've been very open about it, but I don't think they actually publish all of their tools and all of their tests, which makes sense if you're a business, right? So if you publish your fuzzer and you tell people, this is exactly what we tested, that's a springboard for hacking into something, right? So, okay, well, what else can I test? So there's it's not just, I think there's a good reason behind it. So we'll talk about the use cases and when you would want to use an open source fuzzer. So if you're offensive, we talked about use mutational. Defensive, generational. If you're business, basically the dollars will tend to work out for a commercial tool. Right, because for businesses, time is expensive. For open source projects, money is expensive. Right? Open source projects have no money. Businesses pay for all their time, and they pay a lot for it. But if your protocol is proprietary or it's obscure and there's no commercial offering, then you need to make your own. And for that, you can either use open source or commercial tools. And if you're an OS project, then you need to use your own or use an open source tool. So about the proprietary one, the businesses will sell frameworks for you to make your own fuzzer, but that doesn't make any sense to me. If we're pouring our own time into making a fuzzer here, and now we're going to have it tied to this proprietary tool, which they might go bankrupt in a few years, or they might increase the price on us, or there might be some licensing issue. So to me, if you're doing your own programming, the open source seems like the best use case for those last two bullet points. What else do we lose besides just those use cases? Well, if the best fuzzers are proprietary, there's not a lot of widespread security knowledge or fuzzing knowledge in particular. And common software security suffers as a result, right? So they sell it to people who can pay for it or who have the motivation to pay for it, and who has $10,000 for their side project to look for bugs that may or may not actually be there. We also lose effectiveness. Open source tools regularly outperform their closed source counterparts. You think of Git, GCC, Linux are all tools that have come up in the open source community that replaced or compete with the tools that came before them. Have any of you guys ever used a C++ compiler besides GCC? A few? Yeah. Yeah, not so hot anymore. And if you still use it, I'm sorry. Nobody uses them because they're no good. You're better off going with the free tool. Obviously, you can do things like inspect, contribute, and improve those protocols so you can have many eyes looking at the details and not just trusting the company that you're buying from. And finally, contributions are driven by user needs. In a commercial environment, they're driven by financial needs, and those, in the ideal case, those needs intersect. In the real world, that's not always the case. So custom network protocols, fuzzers today, got Beach Fuzzer, split to closed source, not very popular anymore. Soli is state of the art. What you get out of a framework like Soli. Have you guys used Soli before? Anybody? A couple. Okay. Count 3. Yeah, it's fun. What you get out of a framework like that is easy and quick data generation. So you specify the protocol format, and then you get the test cases for free. And it has a lot of instrumentation support. It's extensible, kind of, except for it's really buggy and it doesn't work out of the box and it's not actively developed. Not very actively developed, I should say. And there's a poor responsiveness to pull requests. So as I was doing this, I was trying to use it, find a bug, submit a bug patch and a pull request, and I think I got obnoxious to the developers, and there's 10 or so sitting in the queue right now. So what do you do? What do you do when you have a tool that's not quite there yet and you can't patch it with pull requests? Well, you fork. So I got tired of waiting for those. Too many bugs to use without a serious time investment. So I probably spent, that's the punchline, probably spent a month or so trying to get it to a usable place. So I decided to split it and introducing boofuzz. That's a play on Soli. Get it? Soli, a couple. Yeah, okay, great. So it's Soli. boofuzz is basically Soli plus support for arbitrary communications mediums. In particular, it can do serial tests. So my employer does a lot of ICS things. So we have protocols that run over a serial line, and now you can fuzz those if you want. Extensible failure detection, and I can't get into the details, but it's easier to do than it was before. Better test slugs and far fewer bugs. And I want to put the emphasis on far fewer bugs because literally there's probably 80 hours or more of just bug fixing time. So that's bug fixing you don't have to do if you use it. So that's the tool, and we'll go through a little demo, DIY Fuzzer. And this is maybe not everybody's a network protocol geek like I am, but I think this is the cool part where you get to, if you're, say you're attacking a tool, you can reverse engineer the protocol, figure out what it is, specify the protocol format, get your fuzzer against it, and then attack the tool and find bugs and hack it. So that's where it gets fun. So the plan here is to choose a target, define the protocol, fix all your framework bugs, and fuzz. And hopefully that second to last step is not as big a deal now as it was before. But it might be. I'm sure there's lots of bugs in there still. And so finding a target, we'll use FTP for a demo, primarily because there's a Soli FTP demo that somebody somewhere wrote online, and that's how I used it, how I got started with Soli. So I owe that person a big thank you. It's a text-based protocol, so that makes it easy, no encoding to work with. It's easy target practice because you can find open source projects that implement FTP not very well. So if you want to search for, you can do this yourself, and I think it's fun. So you pick a protocol like FTP. And so how I got it, you search for FTP and you go into advanced search in GitHub, and you can choose, okay, I want something with FTP in the title, so a project called FTP, right? And then I put server in the body to get servers as opposed to clients. And you can filter by language, so C is great language for bugs, right? Everybody likes C, right? So there's the search string if you want to get fancy, but you can do it all through the GUI, so it's not very complicated. And then you can sort by fewest stars if you want to, so you find the most obscure projects first. And it's just target practice. So it's target practice because those projects aren't used for anything, but you can play with them. So this is the boilerplate, and there will be a link to this code online if you want to get it later. Obviously, you import the framework, and those lines are mostly boilerplate, except for the last one, where you specify the IP address, the port number, and then the transport layer protocol, which is TCP in this case. UDP is supported, and a few others. So then we go into the protocol definition. On the right-hand side, there's a back and forth diagram of a FTP session, so it's pretty simple. The code, so moving to the left, there's the code from the server So it starts out saying the server's ready. Then the client says, this is my username. And it says, OK. And then it says, this is my password. The server says, OK. And then you give some command like store, retrieve, there's read or write. And then actually FTP will open another port to send the actual data across, but we're not worried about that right now. So in the actual code, you so S initialize, these are the macros. This code is all the same in Soli. You initialize a block, which is, or rather a request. It gets confusing. So you initialize, that's basically your message, one protocol message. Then you say, I have a string with the contents user, a delimiter of space, and the string with my actual username, and then a static carriage return new line. And so the idea is that you specify what kind of data you're giving to the framework, and it knows how to fuzz a string. It knows how to fuzz a delimiter, and it knows how to fuzz. You can do integers or floating points or whatever. So you specify the data, and it knows how to attack that. So you're not constantly writing, oh, I want to try the string, I want to try the null character, I want to try 10 null characters. And then static will not actually get fuzzed by default, so because that's our end of message marker. And then actually every message looks the same, so it's pretty easy. So pass is the protocol, what you call a keyword, and then James is our password here. Then we specify the store command. Again, same thing, store, the name of the file name of the file. RETR is retrieve. Again, what file you're retrieving. And that's it. And then you actually link the messages together, so you tell BooFuzz what order they go in. So here you have users first, then pass. And then you can see in my high-tech diagram made with Visio, not really, you store and retrieve, both come after password, so you can, basically there's two test cases. It'll test the store route and the retrieve route. And you could have a more complicated tree if you wanted. And then you fuzz, and then you run Python on your little script, so it should be about 20 or 30 lines for that one. The end. Not really. So as I was doing the slides, I thought I should probably actually run it on something and make sure it works, right? Or have something to show. So target one, the name is redacted because, I don't know, you can ask me who it is later if you want. But you can find it. It's the first repo you find if you're sorting by fewest stars using the string that I had earlier in the presentation. Right. So, we pull that up, you run make. So when I was looking for these repos, my criteria were runs FTP, looks kind of obscure, and it's easy to build. So if it had a make file, it passed the test. So this is the logs from test case 1. There's a lot of details in there, but if you can read it, it's transmitting, so it tells you what it transmits. It says how many bytes it sent. And that's kind of, actually that info line is because your socket might not send all the bytes that you told it to send, so it's just a confirmation. And then it tells you what it received in hexadecimal, and translates it to ASCII, and then it has the check. The only check it does right now is to make sure it actually receives a response from the target. So if you're going to put more time into it, you'd parse that response and make sure it's actually something reasonable. So first test case is OK, check OK, some data received from target. And test case 2, a socket exception. So that's kind of in the framework, bug in the framework, but, well, maybe something actually happened in the server. And you got an infinite loop here. So this is what the server did. So the unhandled exception is a bug, but it actually found a real crash. So that's good enough for me for right now. So the results for target 1, success. The server is in an infinite loop. The offending test case was actually the first one, and you can reproduce it by just running netcat and putting a file directly into the input before you start the server. And so it's actually it's a race condition. Right? So the server isn't. It works if you open the connection, wait a little bit, and then start sending your data. So that's kind of cool. It's kind of lame though because it's not really a packet format error, but still found a bug, so I'm happy. Target 2, another. This one is on the first page when you use that search string, and it has 6 stars, or at least it had 6 stars a week ago, so if you want to find it. It was easy to build, and it wasn't apparently used. So this was the second one that I did, or there was another one in between these, and I found it, and I read it and said, used in production environments. I thought, oh, that's going to be too hard to break, so maybe it wouldn't be, though. So in this one, it actually ran for longer, so we get to see the web interface. This is, again, coming over from Soli. So the web interface will show you progress bars and let you know how many test cases you're running, because the test cases come across hundreds per second or thousands per second. So it helps to have the web interface. So making progress, and then we got another crash. Okay, that's lame. So I need to go catch that exception and do something else with it besides crashing. But again, maybe something happened on the server that's interesting at this point. Just to be clear, this is boofuzz crashing. So, and then this is the actual server, the thing I'm testing, crashing, or not crashing. So it's just normal connection errors. But then down in the middle, there's a stack smashing detected. That's when you have a buffer overflow case, but your compiler has stack protection enabled. And then if I ran it on another server, then I got a whole bunch of these. So that was kind of cool. But that was on a different machine. So there, again, it's most likely a race condition. So it does some kind of threading or connection stuff. And so this one was probably a buffer overflow, which is exciting. Stack protection. Well, I compiled it, so and it's hard to reproduce. So I think there's some kind of race condition again. So that was 2 targets, and that was enough for me just to demonstrate that you can find bugs with it. And the point here is, the point of this talk isn't to show off these cool bugs I found. These were in about a couple days. Just as I was putting the slides together, I thought I should actually use it against something. So the point is, it's pretty easy to go find a project and start hacking into it yourself using a tool like this. And the work would come in unless there's bugs in the framework. That's work. But the work would come in specifying the protocol. So boofuzz is for free, and the FTP sample I have is for free. So you could go crash things with that if you want to. So boofuzz, you get quick test generation. Like Soli, it's extensible. There's less bugs than before. Obviously, it's could use progress, more users, more published protocols. I'm kind of curious to see how fuzzers develop going into the future. Will they stay mostly commercial, or will open source fuzzers supersede them or even become competitive? And that depends on how many people use it. And the biggest use case for that is somebody who's employed by a business or somebody who wants to do this kind of stuff, and they have the technical background to get into it. Because you're going to need to write your own Python code if you want to get fancy. And you're going to need to be able to figure out what that protocol format is and specify it. So, could use more features as well. So takeaways from the talk: fuzzing is an important testing activity and rapidly becoming normal. Actually, I didn't say that before, but I say it now. It's rapidly becoming normal. Since 2001, the commercial market has been growing for this, and it's for example, there's the Underwriter Laboratories Cyber Accreditation Cap something, and fuzzing is a part of that. Fuzzing is a part of Microsoft's secure development lifecycle. And if you think, oh, Microsoft's no good, well, you're wrong. They've done some good stuff in the last few years. So it's something that's becoming more and more common, and it may be something that's expected, but how common it becomes really depends on where open source can go, because not everybody's going to pay for it, especially open source projects. So rapidly becoming normal, maybe you be the judge. There's no mature open source network fuzzing tools. Good open source tools are critical for secure protocol implementations, whether you're a business or not. And 2 big needs in this realm are improved frameworks. In my opinion, boofuzz is the best one out there, but if you know better, please let me know. And then the other side of that would be published protocol definitions, because that, if you have the framework and the protocol itself, you can download those and you can run your test right away without doing any work. So those are the things that will make it really easy for people to do this kind of testing. So if you're interested, I encourage you to go write your own protocol fuzzer. Getting started is easy. You can write me an angry email if you download my protocol. If you download my framework and there's a lot of bugs, then let me know. So thank you and happy fuzzing. Any questions? Yes? Oh.
Have you fuzzed your target study and compared with it?
Have I fuzzed using boofuzz and Soli to compare the results? I haven't. They'd be the same, essentially. So most of the generation code is the same. And what I've done is fix bugs like the connections not working or getting these exceptions thrown or things crashing or the log being double and logging 2 of everything. So you should get very similar results, at least right now. Yes?
So if I automate the monitoring process for fuzzing, it looked like you were doing manually looking at waterlogged or error messages. If I automated that, I don't want to know what streams to look for in waterlogged or give it iteration of
If you automated the error checking process, how would you know what to look for in the error check?
I know what errors with any given day is likely to generate for any given error.
Yeah, so that's the tricky part. So the question is, if you're writing that failure checker, how do you know what to look for? Like, I mean, if you send garbage, it could crash in 10 different ways or 100 different ways, and it's not easy to figure out. It's not trivial to evaluate whether this data you're getting back is indicative of a crash or a security vulnerability or just a normal error message. Is that about right?
Yeah, right. So I can use several models. I can ping it and see if it's still up, or I can just look at the service and see if it's still up, or I can monitor, do a grep of our log to look within a certain stream. It's those streams, all those streams, relevant error streams that I'm interested in. How do I find those from the data?
All right. Okay, that's a very good question. So broadly, the question is about failure detection and what do you look for. So there, actually, I could have had a few slides about that. So there's a few broad categories. One is what you can see across the network, and that's what you need to use, especially if you're fuzzing another device or another thing that you don't control. You need to look at what comes back at you. So in that sample example slide I had, are we doing okay on time? Yeah, barely. So we had a health check. You send some kind of request and response. And that's kind of the easiest thing where you don't know what to expect from your anomaly. So you say, I'll just send a good message. And it's essentially a ping, right? It's just, maybe it's an HTTP server and you get the index, you get the homepage. And you just make sure that you get the right value back for that test message. So you go anomaly, test case, anomaly, test case. And as long as your test case checks out, you know you didn't break what you're testing. Now that's tricky because you might have broken something and it just didn't cause it to crash, right? So really what you want to do, and this is what takes more work, you want to parse what you get back from your anomaly, and it should either be a valid message or an expected error message. So if your protocol and your system is robust, you really should have only 2 kinds of things that you expect: a valid response or some kind of known error message. Now, if your protocol doesn't specify the error condition, that's a bad on the protocol, right? They didn't specify that. You got an undefined use case. But if you can do that error checking, and it'd be a lot of work, you'd have to parse the message, see if it's expected. So it's not easy. But if you do that, that's actually what Codenomicon did with Defensix when they were looking for Heartbleed. They were implementing that kind of functionality, and apparently one of the places they started was TLS. And so with Heartbleed, you don't actually crash the server, you just get a whole lot of information that you weren't supposed to get, right? So the kind of fuzzing technique I showed you won't do that, because you're going to get all this expected data. So you need to have some kind of code that says, whoa, that's a lot more data than should have been expected. And you need to be really careful about it, because the length field you told it was way too long. So you need to know, you need to be careful, and you need to have some way of knowing what's what's okay, what's an expected error message, and what is unexpected, indicating some kind of erroneous behavior. So that's the best I have for that. And then on the other hand, you have you can monitor the process if you have debug access to it. So there's tools in Solely and by extension in BooFuzz, but I might have broken them, but give it a try first. You can run something in GDB essentially, and then monitor the process to see if it crashes. And then that's kind of cool because you're looking at the process itself. Or you can monitor for crashes or some kind of unexpected behavior. Or you can look at syslogs or server logs. There's actually a lot of different things you could do. So the commercial products will have places where you can hook in your own scripts to look for those kind of failure conditions. So it's not easy, I guess, is the answer. But very good question. That's an excellent question because that's where it really gets tricky. And if you're buying a commercial tool, you need to make sure they have good support for that because you basically need to hook in your own programs. So to really do fuzzing well, you can't get away from programming. Okay. Yes? What's that? What are they? So what are the two projects there? Okay. BooFuzz, So BooFuzz is the framework, and then BooFuzz FTP has that sample code I just showed you. So if you download both of those, and if you install BooFuzz and download the FTP one, you can run FTP and start fuzzing a server right away. So you would need to have, in an ideal world, there would be all sorts of projects for all different protocols. So FTP is lightweight. It's also kind of a demo. It's just a few messages it tests. Thank you. Any other questions? Any other questions? Cool. Thank you very much, guys.